Welcome to your Introduction to Statistics, Unit 5, Lesson 1. Today you're going to learn to use the empirical rule for normal distributions, and you're going to learn to convert between z-scores and raw scores, and you're going to learn what those things mean. Okay, the values in a quantitative variable follow a distribution that if you made a histogram and then you drew a curve over it, looks like so. It has the following characteristics. Then we say it follows a normal distribution. So if you notice one thing, the curve is what's called a bell-shaped curve, and the highest point, the peak, is going to be over the mean, mu. Because it's symmetric, the mean and the median would be the same. Again, the curve is symmetric or symmetrical about the vertical line through mu. They're mirror images of each other, the two sides. And the curve approaches the horizontal axis but never touches or crosses it. It just gets closer and closer and closer. The transition points are inflection points between curving upward and downward. See, this part, it curves upward, and then it starts to curve downward and curves downward, and then starts to curve upward. Those always occur one standard deviation away from the mean, which is really cool. So the inflection points are at mu minus sigma, so the mean minus one standard deviation, and mu plus sigma, so the mean plus one standard deviation. There is something called the empirical rule, and it applies to any normal symmetrical and bell-shaped distribution. Approximately 68% of the data values lie within one standard deviation of the mean. So between where those two inflection points occur, you're going to capture about 68% of the observations. If you go one more standard deviation to the left and one more standard deviation to the right, where you're two standard deviations away from the mean on either side, you're going to capture 95% of all the data values. If we go one more standard deviation, we're going to capture almost all of them. About 99.7% of values will be within 3 standard deviations of the mean. Let's look at an application. The life of a particular type of light bulb is normally distributed with a mean of 1100 hours and a standard deviation of 100 hours. What is the probability that a light bulb of this type will last between 1000 and 1200 hours? Well, that's one standard deviation below the mean, because 1100 minus 100 is 1000, and one standard deviation above the mean, so 1100 plus 100 is 1200, and so about 68% of the observations are going to fall between those two values. Okay, there is something called the standard score or z-score, and it tells you how many standard deviations above or below the mean a particular raw score or observation is. So the z-value or z-score again tells you the number of standard deviations between the original measurement and the mean. It's in what's called standard units, and it's x minus mu over sigma. So it's the observation minus the mean over the standard deviation. If the observation is exactly equal to the mean, it's going to have a z-score of 0 because your numerator would be 0. Because these two would be the same. That makes sense. If the original score is bigger than the mean, your z-score is going to be bigger than the mean. And if the original score is less than the mean, of course, the z-score is going to be less than 0. Okay, so let's calculate a z-score. The amount of time it takes for a pizza delivery is approximately normally distributed with a mean of 25 minutes and a standard deviation of 2 minutes. Convert 21 minutes to a z-score. So we're going to use our formula of x minus mu over sigma. Our observation is 21, so that goes in for x. The mean is 25, so that goes in for mu. And standard deviation is 2, so that goes in for sigma. So you end up with -4 over 2, which is -2. So that would be 2 standard deviations below the mean. That would be a really fast delivery. All right, the mean delivery time is still 25 minutes. The standard deviation is 2 minutes. Convert 29.7 minutes to a z-score. So we do the 29.7 minus 25 over 2, and we get 2.35. So this was a long delivery. It took 2.35 standard deviations above the mean. Now, we can work backwards to get the raw score. Okay, it's just the result of converting from standard units, the z-scores, back to the original measurements, the x values. The formula for this is just an algebraic manipulation of the z-score formula, and it's x equals z times sigma plus mu. All right, so if the mean delivery time is still 25 minutes and the standard deviation is still 2 minutes, interpret a z-score of 1.60. So we want to know the delivery time that is 1.6 standard deviations above the mean. So we're going to use our formula of z times sigma plus mu. So that's going to be 1.6 times 2 plus 25, so 3.2 plus 25, so 28.2 minutes. All right, that's it for lesson 1. Go ahead and do the problems to try on your own. Make sure you have those ready to go when you come to class. Thank you so much for watching the video and taking good notes. I hope you have a great day, and I will see you soon.